We're now going to go ahead and take a look at solving exponential equations. And they are equations where our variable is in the exponent, hence the name exponential. So, looking here on the left, we're going to go ahead and solve this. It's an exponential equation because we have a variable as an exponent. We're not going to do anything to the problem on the left, or part on the left. However, you'll notice the part on the right, if you remember your powers from earlier, this is really a 4 to the fourth power. We want to try to get the same base on each side. The left side was 4 to the power. We wanted to try to get the right side as it was 4 to the power. If we can get the same base on each side, the only way they're going to be equal then, with the same base, is if the exponents are equal. So we can basically drop the bases, set the blue exponents equal, and we can solve that. Add 2, divide by 9, and we get 2/3. So our answer for this one here is 2/3. So if you plug the 2/3 in for our n, 9 times 2/3 is 6, minus 2 is 4, and 4 to the fourth power is 256. Same idea here on the right. We want to try to get the same base on each side. The left side is already 2 to the power. Can't really do much to that, but 32, remember, is a 2 to the fifth, still all raised to the x minus 5. We now have 2 to the power on the left, 2 to the power on the right, so we should be able to drop the bases. So we're going to take the exponent here on the left, set it equal to our exponents over here. Remember, an exponent raised to an exponent, you multiply them together. And then we're going to distribute through. And then we're going to get the x's on one side by subtracting a 3x. Then we're going to go ahead and add a 35 to both sides. You get 36, divide by 2, and we get 18. Same thing is true when you're dealing with inequalities. This is 5 to the power, so we're going to leave that as 5 to the power. We can't change our base. This is really a 5 to the fourth on the bottom, but it's on the bottom, so if we bring it up, it's really a 5 to the negative fourth. We get the same base on each side, so then all we have to do is deal with the exponents. Take our exponent there, take the inequality sign as we see it, take our negative 4 other exponent, and then we solve it by subtracting 3, divide by negative 2. Remember to switch your inequality sign. And so we get x to be less than 7/2. Same idea over here. 3 to the power on the left. This is a 3 cubed on the bottom, but we need it as 3 to the power, so we're going to bring that exponent up, so it becomes a 3 to the negative 3. Same base, so we can just deal with the exponents. And we get k is less than 3. Now, sometimes you're going to be given 2 points, and you need to find that exponential curve that goes through those 2 points. Now, remember, when our x was 0, that tells us our y-intercept. And our y-intercept is 5, and that always tells us what our a value is. So we can go y is equal to 5 times our unknown b value raised to the x. Now, all we have to do is take our other point and plug it in. So here, this other point, our x is 3. So I'm going to plug in 3 for x. And our y value of this point is 125. So I'll plug that in for y. So I get 125 equals this. Now all I have to do is solve this. So I can divide both sides by 5. Then I can take the cube root of both sides. So I get the cube root of 25. Remember, 25 is a perfect square, so we can't really simplify it beyond that. Now, if you wanted, you could write it as a 5 squared, then raised to the 1/3 power and multiply the exponents, and you could write it as 5 to the 2/3. Either one of these would be acceptable. So now we're going to plug our a value, which was 5, and our b value back into the original problem, leaving our x and our y in our problem to write our exponential equation. So we'll go y equals our a value, which was 5 from what we had figured out up here with the y-intercept. And then our b value, which was the cube root of 25, all raised to the power of x.